Given two kids on a massless seesaw with a total length of 6 meters, if the mass of one kid is 25 kilograms and the other is 35 kilograms, how far from the heavier kid will the seesaw balance with the two kids at opposite ends? So since it says balance there, it looks like this is a balance type of question. And we've already recognized that the center of mass really is the balance point. So maybe somehow calculating the center of mass of these two kids on the seesaw is going to help me to figure out where I want to place like a some kind of support or like a fulcrum, right, to have the seesaw balance upon. So let me kind of draw a picture of this here. Let's say this is the seesaw. Okay, and I think I'll put the bigger kid here on the left. Okay, so that's the 35 kilogram kid right there. And I'm not very good at drawing kids, so my kids are just sort of blobs. But don't tell any kids that I called them blobs, okay? Anyways, so they're 6 meters apart, right? So the total distance between these two is 6 meters. I don't know, I was going to draw that in there, but I'm not sure if I need to. I think it's clear enough, right? And the real question I have is, I think, I'd want to place the fulcrum, I think, closer to the larger kid in order for this to balance, right? And maybe a way of looking at this is, since I'm wondering how far to place this from the big kid, but really this point right here, isn't this just the center of mass point, right? That's pretty much what I was saying as I was kind of talking this through and drawing this sketch. So maybe I can get the answer to this if I choose an appropriate coordinate system in which to calculate that center of mass point. In particular, right, I think the distance that corresponds to the question is that distance. So that distance will be xcm, as in the formula that we use for that, provided that we use an origin that is right there, right? So that means that if mass m1 is equal to 35 kilograms, position x1 will just be at the origin, so 0, and then the lighter kid with the 25 kilogram mass, that kid's position will be x2 for the formula that I'm going to use, and we'll make that equal to 6 meters, right? So now I'm ready to calculate using the center of mass formula for two objects. Okay, cool part is this part right here just goes right to 0, because x1 is equal to 0, so I'm not even going to have to do that one. I'm just going to have to do like 25 kilograms times 6 meters divided by the sum of 35 kilogram plus 25 kilogram. I guess I could have just put 60 kilograms there, right? So 25 times 6 divided by 60 is what we're looking at here. And my calculator says 2.5 meters. And that makes sense because that's, as we kind of predicted, that's a little bit closer to the big kid than the littler kid. It kind of reminds me, I mentioned, I think, 1 or 2 videos ago, the name Richard Feynman in the Feynman lectures. And I'm not sure if I'm going to get this quote exactly right, but Feynman said at one point that a physicist should know the answer to a question before he or she even calculates it. And to some extent, me having drawn this picture and already made somewhat of a prediction as to where I think that center of mass point, and then getting this number and being able to say, oh yeah, that kind of makes sense, that's kind of part of that. So that's a really important part of problem solving in physics. And there are a myriad of ways of doing that. So part of my philosophy is, like, we do a lot of problems and I kind of show you some of the tricks that I've picked up, and you want to be picking up those tricks too. I have seen some examples where people will say, hey, do just these 3 things. But that's not always good, because I don't think you can boil it down to just 3 possible ways of checking whether the end of your problem makes sense with the beginning. In other words, does your answer really check out with what you think should have happened?